Alright, so this chapter is polymers. Polymers, they have a wide range of properties, and it is very easy to play with the chemistry of the polymers, the structure, to achieve different type of properties. Okay, so polymers, they have advantages. Advantages such as when we compare them to metallic materials, first of all, they are have low cost and they have ease of manufacturing. What does it mean? You can easily color them, for example, easily shape them, and they are also lightweight compared to metallic materials. So we're gonna see the structure of polymers and how we build the polymers, actually how we process them, what is crystallinity of polymers, and how this affects the properties, their glass transition temperature. Unlike other materials where they have a constant melting point where they go from solid to liquid, polymers have glass transition temperatures where they translate from a rubbery state to a brittle state. So we're going to learn about mechanical properties and two types of properties we generally categorize polymers to, like thermoplastics and thermosets. There are also elastomers and application advantages and limitations. I should say usually they use the term polymers and plastics as something representing the same material, so we will keep that in mind. It's a synonym for polymers, plastics and polymers. Okay. So where do we see polymers, right? In food and beverage containers, water bottles, packaging, houseware, housing of computers, monitors, textiles, medical devices, foams, paints, toys, appliances, lenses, electronic and electrical products, everything pretty much. Why? As I said, they have relatively low cost and ease of manufacturing. They have resistance to chemicals. So therefore, when they carry chemicals, they usually put them in polymer or plastic bottles. Low electrical and thermal conductivity, low density, high strength to low weight ratio. So some polymers can be engineered in a way to have better strength values. Noise reduction, wide choices for colors and transparencies, complex design possibilities, and they are capable of being molded and shaped. The bad thing is low strength and stiffness. So remember, strength to weight ratio is something different than having a low strength. So they have high strength to weight ratio. Let me see. So there should be not any low here, right? Strength to weight ratio is high, but then they have actually low strength and stiffness, high thermal expansion coefficient. The worst thing about polymers, I would say, the temperature range that we can use them. So because they have very low melting points, or basically softening temperatures, they cannot be used at high temperatures. That's why it limits their usage in aerospace industry, basically. And they have lower dimensional stability because they have a very porous structure. They can absorb moisture from environment, and they are sensitive to sunlight. They can change their dimensions, degrade. So those are causing lower dimensional stability in polymers. So in these tables we will see different type of polymers and their properties. Okay, so what are their strength, moduluses, ductility, and Poisson's ratio? Like nylon, the common ones we see. So nylon, polyethylene, polypropylene, and polystyrene, polyester, polycarbonate. Okay, so it continues as epoxy, polyester, silicone, urethane. As you can see, the plastics, they are separated into three groups here. Thermoplastics, and these are all thermoplastics, and thermosets like epoxy, elastomers like rubber, silicone. These are elastomers, and we're gonna see the characteristics of each those types. So what we're gonna see in this chapter that is outlined here. So poly means many, right? Polymers, many mers here. Okay, so mers are gonna be the repeating unit, building unit, the smallest repeating unit of these materials, and poly means many. Okay, many of these building units coming together and forming a large molecule. It's called micromolecule. And how they are formed: with some heat, with some pressure, some catalyst, with processing that we call polymerization. These little mers attached into each other, forming many mers or polymers, and forming the general structure we know. Okay, so polymers, in it we add fillers, plasticizers, stabilizer, colorants, flame retardants, lubricants to the polymer to change their properties. And polymer structure can be amorphous, crystalline, partially crystalline, linear, branched, homopolymer, copolymer, terpolymer. So we're going to see all these are. So we group polymers or plastics into thermosets, thermoplastics, and elastomers. So the commonality between thermosets and elastomers is what we call cross-linking. Cross-linking is between these micromolecules. There will be additional bonding we're gonna see. And we are also given in this chart that like epoxies are thermosets, rubbers that we use in car tires, for example, they are elastomers. And everyday polymers like polyethylene, PVC, polycarbonate, nylons, these are thermoplastics. The properties of polymers depend on the structure of the individual polymer molecules, and molecule shape, size, and arrangement of the molecules in the structure. These are very large molecules, very large size, and also called micromolecules, as I said, which distinguish them from other organic chemical compositions. So those long chains are formed by polymerization. So large molecules, also we call them long chain molecules, they are formed by polymerization. So monomer or mer is, as I called, is the building unit of the polymers. Okay, and we're gonna see what those are. For example, let me give you an example here. Let's say the monomer of a polymer polyethylene is gonna be this carbon-carbon bond, and of course carbon needs to make 4 bonds on all sides, right? Remember, this is covalent bonding. So actually, let me see, these are gonna erased. So the smallest building unit of polyethylene is this. So n times of that come together and attach to each other. right? Another one of these come, and long chains, long molecules with a carbon backbone, long one, okay? This goes like a lot, long. These are hydrogen bonds. So this is polyethylene, okay? When I always try to understand polymers, think about this chain as a string of, for example, there is a string of a spaghetti. So think about this is just one string, right? This is the carbon, this is the chain we have, one string from a ball of spaghetti, let's say. And of course we will have, so all these are carbon, 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 right? With different side chains, hydrogen, hydrogen, hydrogen. And this string will come together with many of these, okay? So it's gonna be like that. This is one, this is another, this is another. Think about spaghetti, okay? This is another. So polymer structure is like that. A lot of carbon chains are coming together, building the overall structure. Each of these chains have a carbon backbone, and there is a smallest repeating unit in all those chains, and that determines the main chemistry. So these hydrogens can be replaced with chlorine, fluoride, like those elements, silicon, and you can change the main chemistry. Okay, so how do we make those chains longer? By repeating these building units. We call that a polymerization reaction. There is two types of polymerization reaction. One is condensation polymerization, and the other one is addition polymerization. Okay, so we seeing that molecular structure of various polymers, and what are the basic building blocks? Monomers. Of course, the monomers are added to the reaction. They have a double bond, carbon-carbon, but it is open during the polymerization, and repeating unit is shown for different types of polymers. Basically, if you have polyethylene, you have hydrogen attached to the carbon backbone, and if you have polypropylene, one of those hydrogen is replaced with CH3. If you have PVC, one of those repeating unit hydrogens changed with chlorine, etc. It goes and goes and on, okay? So we are seeing the Teflon structure. As you can see, the main backbone, the main chain is a carbon-carbon bond, okay? And as you see, all polymers named with poly, right? So many repeating unit, and the side atoms that are attached to the carbon is changing. So depending on that, all those different properties can be achieved by different type of polymers. Okay, so we are seeing here is different polymerization. So how those mers or repeating units are attached to each other. Okay, so one is condensation, another is addition. Okay, so in condensation polymerization, polymers are produced by the formation of bonds between two types of reacting mers. So we see are in the image different type of units reacting together, and as a side product HCl condensates. That's why it's called condensation, and the nylon chain forms, as you can see. So this is condensation. No need to know more details. This is more like people who know organic chemistry do those type of reactions. We don't have to understand every detail, but we need to get a general idea. So in the addition is we start with the here there are no condensation byproducts like HCl acid, but in that case we start with the repeating unit MERS and then apply heat pressure catalyst to open up that double bond. Therefore, quickly each of these MERS are attached to each other, building the overall molecule polyethylene. So how do we define molecular weight? Molecular weight of a polymer is actually the sum of molecular weights of the repeating unit MERS in the molecule. So what is the molecular weight of each repeating unit? Times N. So actually each molecule, think about a plate of spaghetti, right? Each have different lengths. Each string have different lengths. So since the N varies with each string, different molecules in a batch, actually molecular weight is just an average volume. And for polymers such as polyethylene, polystyrene, it is around 3000. And the polymer's molecular weight and its distribution have a major influence in its properties. So because there is a variation in the length of each chain in the batch, so there's going to be a molecular weight distribution, right? So therefore another term here, degree of polymerization. So degree of polymerization is giving us basically the number of monomeric units in the micromolecule or the polymer. Of course, this can be found as the ratio of the molecular weight, the overall molecular weight, to the molecular weight of a single unit. This will tell you how many units are there, repeating units, in a single macromolecule. So why the degree of polymerization is important? Because higher the degree of polymerization, higher the mechanical strength, higher the viscosity. Viscosity is the material's resistance to flow. This can affect processing, right? And high adversity, as I said, adversely affects the ease of shaping because there are mold cavities and we want this fluid to flow. But polymers are, if they are high viscosity fluids, then they won't be easily flow through those mold cavities. Okay. So bonding is important because I told you guys monomers are linked by covalent bonds. As you go back and see, these are all covalent carbon-carbon covalent bonds, right? But so each of these chains, within the chains there is carbon-carbon bond. And carbon-carbon bond is very strong, but polymers are weak. The reason is mechanical properties are mainly controlled by the bonds between the chains, what we call the secondary bonds. These are hydrogen van der Waals bonds in between the chains. So chains are attached to each other also with weak bonds that are holding the structure. So these weak bonds are actually breaking when we are trying to shape polymers. So the strength of the secondary bonds determine the overall strength of those secondary bonds. Can be made stronger like covalent bonds if you attached the chains with covalent bonds also, so you will create a very strong structure. In this graph we are seeing how molecular weight and degree of polymerization is affecting the properties such as tensile strength and impact strength and viscosity. And as we see, if we increase the molecular weight and the degree of polymerization, the viscosity of the polymer is increasing. And of course, its tensile and impact strength is also increasing. So there are different ways the chains can form. There are different ways the monomers attach to each other. And based on that, the polymers are divided, based on their structure, they are divided into 4 categories. One is linear, the other is branched, the other one is cross-linked, and network. We are actually seeing example easily to figure out how each monomer, if you assume each of these balls here, each are monomers. If they attach to each other side by side, they are linear polymers. Those are usually the structure of thermoplastics, such as polyethylene, PVC. It can also be branched. Think about a tree branch, right? So new side chains are attached like this, okay, to the main chain. And of course, this type of branch structure, so the linear polymers, if we go back to linear polymers, they are very simple structure, right? But if we go to the branch structure and think about 3 branches, right? These structures, if we try to pack those chains next to each other, if we try to pack those chains, there will be some resistance to having a highly dense packed structure because of those side chains, right? They will entangle with each other. Suppose there is another chain with a side chain here and here, and they will entangle. So those entanglements of branches make those chains difficult to move around, and this also strengthens the polymers, okay? Because if they cannot move around easily, you are increasing the resistance to deformation. But of course, as always with other materials too, if we increase the resistance to deformation, we are making them more brittle. So stress cracking is increased because relative motions of molecular chains is limited. So when it comes to cross-linked chains, these are usually for thermosets, rubbers, and some elastomers also have cross-linked structures. What happens there is the chains themselves, right? They are attached to each other, not with weak bonds, but strong covalent bonds. So the motion of each chain relative to each other, they don't slide over each other easily, so that affects their deformation. They are very strong. Okay. But once the structure is cross-linked, there is no turning back, meaning you cannot break those links and get a easily flowing structure. Cross-linking has a major influence on the properties. It increases hardness, strength, stiffness, of course, brittleness. It provides better dimensional stability. So this process actually in our car tires, the rubber is vulcanized. It's called vulcanization. That is actually the forming of these cross-links in between the chains. So this way we achieve strength. So the network is, these are three-dimensional networks. As you can see, a highly cross-linked polymer. So these cross-links can be induced with subjecting the material to high energy radiations, ultraviolet light, X-rays, and electron beams. So what we are seeing is how the elastic modulus is changing with temperature. So Tg is the glass transition temperature and Tm is the melting temperature. So we are seeing, first of all, glass transition means that at certain temperatures below the glass transition temperature, the material is behaving like a glass, so brittle material, and above that it's rubbery, more viscous. Okay, so melting point in polymers only observed when there is crystallinity in the structure, and if you keep increasing the crystallinity, as you see, they are having more towards having a certain melting temperature. As you can see, elastic modulus is decreasing with increasing temperature. So the material goes from more leathery state to rubbery state and then a viscous state. Of course, this again depends on the degree of crystallinity, right? So if there is some crystallinity in the structure, if we compare it with 100% crystalline material, which never observed in polymers, 100% crystallinity is not possible because of the large molecular structure. Basically, they cannot arrange in a perfect order like in crystalline materials, right? So because of this weak bond is sensitive to the temperature, basically if we have 100% crystallinity, that with temperature the material is preserving its glassy state, but then if we have more amorphous regions with temperatures, the modulus is decreasing due to the breakage of these intermolecular weak bonds, basically. Same is true with the cross-linking, right? If there is no cross-linking, material will easily flow, the change will easily flow on top of each other, and the material will go from leathery to rubbery and then viscous state as we increase the temperature. But if we increase the cross-linking, the material will be more strong, more behave in a glassy, more strong, brittle state, glassy state. So these glassy, leathery, rubbery, viscous, think about those are like if it's a rubber, it's easy to deform, right? Leathery, it's a little bit more difficult to deform, not like rubber. So those are giving you information about how the polymer is behaving. Okay, so glass is more brittle polymers, more strong and brittle polymers. So this summarizes the things I told you guys. So linear polymers, because they are simple structures, they can be easily arranged into more crystalline structures. Okay, but as the chain configuration gets more complex, like branches coming out, cross-linking. Those type of the structures are difficult to arrange into crystalline regions. So linear polymers are more susceptible to forming crystalline structures. So branch polymers, as we said, side branches are forming, resistance to deformation is increasing, therefore stress cracking is increased. The density is lowered because they cannot pack easily like linear polymers. Cross-linked polymers are the adjacent chains are linked by covalent bonds. Those are usually thermosetting polymers like epoxies, phenolic silicones. This cross-linking gives the material hardness, strength, stiffness, but of course gives also brittleness and better dimensional stability. And there were also network polymers, 3D network forming chains. So polymers are never 100% crystalline. So crystallinity means there is a long range order in the packing, atomic packing, right? But there can be certain crystallinity. We call them semi-crystalline. So also polymers mostly amorphous. There is no long range order in the structure. These are like polystyrene, polycarbonate. When there is a big side chain, like in polystyrene, there is a big side chain, a big side molecules. These molecules are preventing packing in a certain order. More complex monomers. These type of polymers will not be able to pack into a crystalline configuration, ordered configuration. So when we say crystallinity in polymers, we are talking about regions that are, let me see if there is an image here. This one, right? So there's amorphous regions where there is random orientation of molecules and monomers, but there are among those structures there is also crystalline regions. We call them crystallites. You see certain alignment, certain packing in an order of these monomers, these chains. Think about folding a fire hose in a cabinet. Okay, so it's like two-phase material, right? One crystalline region. Of course, these crystalline regions will have different properties than amorphous regions. Okay, so as the crystallinity increases, polymers become stiffer, harder, less ductile, denser, less rubbery, more resistant to solvents and heat, which is expected, right? So the increase in density is expected with increasing crystallinity because within a certain space there are more amounts of units, more packing, more dense packing, right? So the density is increasing. So this is called crystallization shrinkage. Okay. Optical properties are also affected because crystalline regions will interact light with differently than the amorphous regions, and this will cause changes in the optical properties. So here is again the definition of glass transition temperature. So why this is important? Because in the manufacturing of polymers, you will need to talk about the glass transition temperature, not the melting temperature, because many polymers are amorphous or highly amorphous, and they won't have a specific melting point. So this is important in shaping them, right? So the glass transition temperature Tg, shown in the figure. So if we start with, in this case, the specific volume is shown. It is decreasing as with decreasing temperature, and sharply decreasing, and more shallow decrease here, because we are going to a more glassy region. So below the glass transition, the material will behave glassy. Okay, that means they are becoming more brittle. So why this is important? Because the glass transition temperature can be the room temperature, and at room temperature the material might be glassy, brittle, right? So we need to be careful what the glass transition temperature is, and what the actual working conditions, working temperatures of that material is. So this will create, if the material is going to behave like a brittle material or more rubbery material. Actually, if you guys remember, there was Challenger space shuttle disaster. Why it happened? Because the rubber normally can act as a seal because of its rubbery behavior, but at the time of the launch, that day, it was cold temperatures, and it went below the glass transition, and the material was behaving brittle, so it didn't seal, and that's why the catastrophe actually happened. So it is important to understand this temperature, and this temperature is going to change depending on what type of polymer is. It is affected also by the cross-linking, the strength of the intermolecular bonds. All those type of things can affect the glass transition. Composition, the chemistry, of course, affecting the glass transition temperature. So in this table we are given different types of material: nylon, polyester, polyethylene, and PMMA, polypropylene, polystyrene, PTFE, PVC, rubber, all those, and their glass transition temperature. Okay, so below those temperatures the material is brittle. Okay, so let's see, their melting points. Okay, so the melting point is, again, if rather the material has like a more crystalline regions, more ordered regions, we can also talk about the melting point. Okay. So sometimes we obtain polymer blends because we want to combine different properties of different monomers and obtain different type of properties. So therefore they blend the monomers and they obtain different chemistry basically. Because amorphous polymers are brittle, they are reduced by blending them with other types of polymer units to enhance their toughness and impact resistance. And thermoplastics. Well, the main thing about thermoplastics, they are easy to shape and mold into desired shapes. And then this process is reversible, meaning you can soften them with heat and mold them into desired shapes, and when they solidify, you can use them, and then you can recycle them, meaning you can soften them again with heat and shape them again into another shape. So you can reverse this process. And of course their behavior is affected with temperature and what is the deformation rate is, how fast you deform them, how slow you deform them. Metals were also like that, right? The deformation rate was affecting their mechanical behaviors. So that's why we say thermoplastics are actually recyclable, because they can recycle into different shapes. So in this figure we are seeing general behavior of three types of different polymers. So one is rigid and brittle. They have high modulus, stress strain curve. You can see there's high modulus, and they go up to high stress values, but what happens, they doesn't have any ductility, they are brittle, because we need to understand the ductility is read from the strain axis, right? How much you can strain them. And there are also tough and ductile ones like nylon, and they can of course go to higher strain values, they are ductile. And they're also the energy absorption, which is the area under the curve, is giving us the toughness, energy absorption, right? So there are also soft and flexible polymers like polyethylene, PTFE. They can deform to large extents, but they are not as strong. So we are seeing the effect of temperature on the strength and ductility. So what we are seeing is that the strength, and from the stress strain curves, the strength and the modulus of elasticity of thermoplastics, they decrease with increasing temperature, because the slope is the linear region slope is the, remember, modulus, and it is decreasing with increasing temperature, which is expected because the bonds are getting weaker in between the chains, right? So, but the ductility increases, easy to deform, easy to stretch, because those chains slide over each other easily. Okay. So here is a graph showing us an experimental result, how the temperature is affecting the impact strength, and we see even small changes in temperature can have a significant impact on the impact strength, significant effect on the impact strength. So you can see with temperature, the impact strength is increasing. Again, this is because the strength is lowering, and the material can absorb more energy, because the absorbing in the energy of inside the material happens with the relative motion of molecules, right, sliding over each other. If they move, they are doing work absorbing energy. So therefore, with increasing temperature, their impact strength is increasing. They are easier to store energies, and they are less brittle, etc. Well, just like metals, there is necking during the tensile test. We are seeing a sample for the tensile test of a thermoplastic, and data is recorded, stress strain curve is given to us, and we can see the necked region of the specimen is elongates considerably. But this happens unlike other metals, right? So these materials can undergo to large deformations before they actually fracture, and that is what the stress strain curve is showing us. So another thing that is being happen for sudden decrease in the strength here is, actually think about, so the molecule is like this, right? When you apply tension, what happens, these chains arrange into like this, more orders stay, they elongate along the direction of the stress. Okay, so when this orientation happens, of course the molecules more easily slide over each other, so there will be a decrease in the strength here, and then they continue to easily slide over each other within a constant stress. so they are not getting stronger as metals. Therefore, you can keep the same strain rate with the same stress. Therefore, the stress rate is constant until some region where a more crystalline arrangement is happening, because the crystals are now more arranging into more ordered structures, which causes sudden increase, but still the polymer goes up until the fracture and elongates to a large extent here. So as I described you guys, when we deform the polymer, the molecules actually align themselves in the direction of elongation. And this makes them anisotropic. The properties will depend on the direction then. The material will become stronger and stiffer in the elongated direction than its transverse direction. So actually stretching is a technique to enhance the strength and toughness of polymers, especially in the production of fibers. So creep and stress relaxation. We know the polymers are susceptible to creep and stress relaxation. Stress relaxation is when we strain the material and kept under constant strain, like in the case of creep, right? The material is under stress. It is time-dependent decrease in stress. Basically, inside the material, the stress is relaxed with time. So of course this changes the dimensions of the materials and the behavior of the material. So another thing is crazing. Crazing is when subjected to tensile or bending stresses, thermoplastics develop localized wedge-shaped narrow regions called crazing. And there is also stress whitening. Think about you are bending water bottle, right? There will be white regions forming. So those are called stress whitening because of how the molecules changed on that region and the changes optical properties basically. Also water absorption, right? So polymers we see it's very porous structure, right? There are lots of pores in between the chains, and those are susceptible to absorbing moisture from the environment basically, and this affects everything, right? Because then the glass transition temperature changes, yield stress changes, elastic modulus, they all lower. That's why polymers, they are susceptible to water absorption, and that's why they are not good materials for using outside in atmospheric conditions. They also degrade with the sunlight, UV lights. You might have noticed that if you have shoes made up of polymers like sandals, leave them outside, actually leave one of them outside and kept the other one inside, so you will see with sunlight how the color is changing. Okay, polymer is degrading. Okay, so thermosettings is where there is cross-linking, carbon bonds between, strong bonds between the chains. Of course, this prevents chains from rearranging during the deformation, right? When we stretch, they cannot align like this. The thermosets do, and they cannot therefore flow easily over each other. So this of course gives them strength, but this process is also called curing, which is irreversible. So these materials cannot be recycled, unfortunately, and many polymers used in composites, they are thermosets, and therefore it is difficult to recycle. There are ways people are working on, like chopping them, using them and somewhere else as a filler element, a filler material, etc. The strength and hardness of thermosets are not affected by temperature because it's a stable structure basically. If the temperature is raised, thermoset polymer will begin to burn, degrade, and char. So thermoplastics, they soften. They can shape into different shapes. They can mold into different shapes. But thermosets, they cannot. Usually we put them in, give them a shape, and then we cure them, form the cross-linking. They cannot soften. They just burn, degrade, or char. Thermosets, of course, compared to thermoplastics, have better mechanical, thermal, and chemical properties, electrical resistance, and dimensional stability, due to the just being the presence of these covalent bonds in between the chains. And sometimes additives are added in the formation of plastics. These are plasticizer, colorants, fillers, flame retardants, and some other additives. So plasticizers, these are added to polymers to impart flexibility and softness by lowering their glass transition temperature. They reduce the strength of the bonds in between the chains and therefore make the polymer flexible and soft. And colorants, of course, these are added to give color, right? Dyes, pigments. Fillers. Fillers may be added to improve strength, hardness, toughness, abrasion resistance, dimensional stability, stiffness. Fillers are usually wood flour, silica flour, or silica powder, clay, talc, calcium carbonate, etc. Of course, flame retardants. Of course, if the temperature is sufficiently high, polymers can ignite and burn. And therefore, this flammability can be reduced by making them less flammable by adding compounds like chlorine, bromine, phosphorus. Okay, so other additives can be. So, as I said, most polymers are affected adversely by UV lights from sunlight on oxygen. They weaken and the primary bonds break, and there is the splitting of the long chains. So polymers basically degrades, and it therefore, to provide a protection against the UV, is we add carbon black. Okay, so actually the addition of carbon black to rubber is the reason why the tires are in black color. Again, these tables are not for memorization, but to give you a future reference. So for plastic products where you have a certain design requirement like mechanical strength, wear resistance, and also we are given its typical applications for those requirements, and what type of plastics would you use for those design requirements. And some trade names, famous names for the polymers. Actually, for example, Kevlar, we know it's an aramid fiber, Kevlar, and some other Teflon is actually a polymer, fluorocarbon, and some other trade names that you might be familiar with. So what are elastomers? So we learn about thermoplastics, thermosets, and there's another group which is elastomers. So what are these? So these are again amorphous polymers with low glass transition temperature. They are characterized by their ability to undergo large elastic deformations without rupture. The one example always keep in mind to understand elastomers is rubber, right? You stretch it, it goes to large deformations without rupture. These materials have a low modulus. Low modulus, of course, means you can easily stretch them. And then they also, as I said, have in the structure they have cross-linking. But compared to thermosets, they have fewer amounts of cross-linking, which makes the structure more ductile, more flexible. Okay. And they can recover easily from large deformation. Always think about rubber band. With increased amount of cross-linking, you can change their properties, their hardness. Tires, like rubbers, we use rubbers in tires, hoses, weather stripping, footwear, linings, gaskets, seals, printing rolls, and flooring, all uses elastomers, right? So, one important property of elastomers is their hysteresis loss in stretching or compression. So this clockwise loop we see here in the figure indicates energy loss. So mechanical energy, so we load the material, stretch rubber, right, for example, and unload it, it goes back to its original position. We know that. But also notice that there is gonna be this mechanical energy is converted to heat, meaning there is some energy loss in the structure. Rubber will get a little bit warm if you touch it after you stretch it and release the stresses. It's gonna get a little bit warm because some of these work they introduce to the system by stretching it, molecular motion. Molecules, when they move along each other, move over each other, because of these frictional forces, basically, there is a heat will be generated. So the energy you give, some of them is converted to heat. But this is important in terms of absorbing vibrational energy or sound insulation, because then the system can absorb the energy. So in your book there are further information. Each type of thermosets, thermoplastics are explained. If you guys are interested, you can read through it to get more information. But there is no reason to go into detail of every type of polymer. But understanding their properties, their behavior is important to explain how the structure property relationships, basically. So we learned that polymers are major class of materials, wide range of applications, and if we compare them to metals, they have lower density, lower strength, modulus, and lower thermal and electrical conductivity, but their cost is high, higher strength weight ratios, higher corrosion resistance, higher thermal expansion coefficient. It can come with a wide range of choices of colors, transparencies. It is easy to manufacture them into complex shapes. And we learned that there is the repeating unit. Repeating unit chemistry can be changed. They add to each other with polymerization processes. And their properties will depend on molecular weight, the structure, packing, crystallinity, and the additives that present, degree of polymerization, etc. The two major classes, thermoplastics and thermosets, and there are also actually elastomers. And elastomers are characterized by basically to be able to go under large elastic deformations. So these are the things we have learned in this chapter. Next chapters will be ceramics and composites next week.